Welcome and thank you for downloading this TU Delft podcast.
About these topics from your side. Nope. Okay, then we will continue today with the next topic. Next topic is materials. And after the break I will do something about exploring limits. But first, the first hour is dedicated to materials. Okay, we will have a number of topics. First we will briefly discuss what are materials. Can we bring forward some kind of definition for it? What kind of materials are interesting? And then in particular for aerospace engineering. And then I also will tell a few things about different aspects of materials, like the properties and how to design with it and how to manufacture with it. And then you will see there is a close relationship between these topics. Okay. First question, what is a material? Could you describe a material? Could you give some features of a material?
We need to provide an external sort of
For 1 minute.
what we need to build something.
What you need to build something.
It provides a sort of skin for a skeleton of a structure that you have.
Provides a skin for a skeleton or structure. My question would be, the skeleton itself, is that made of? Other ideas?
A collection of matter that makes up a something.
Collection of matter. Yeah.
Essential things.
Everyone knows when we're talking about materials what we mean with it, but how to formulate and how to express it can be rather difficult.
Basically, some specific density, strength, which can best do the job with.
Material has strength, density, and so on. Yeah, density, weight. Has some properties indeed. Composition of elements. Yeah. Well, actually, to give a very crisp and clear definition, that's rather difficult. Also, if you look into textbooks and also in dictionaries, it is rather complicated to find a very nice, a very neat definition. If we talk about materials, we often have to do with substances, with matter. And all the properties which I've heard already, strength and stiffness and composition, those are related to that material, and it is not related to any geometry. That's the difference, for instance, with a structure and a material. A material has substance, has properties, and a structure has substance, has properties, but these properties are also related to its dimensions. We can talk, for instance, about the strength of a material. We can also talk about the strength of a structure. If we talk about the strength of a material, we can zoom in as far as we can, and still that material has the same property. For a structure, the strength is also related to its size, to its dimensions. Small structure has small strength, large structure has large strength.
I'm sorry, I don't want to interrupt, but wouldn't the fact that yes, that's why I'm apologizing. Wouldn't the fact that it is a material and that it exists, that it would have a shape by its definition? That since it is a material, it has to have a shape. Because without having a shape, it can't be a material. But over here it says, but it's without shape. So it doesn't exist.
Of course, a matter always has at least some dimensions, but the idea is that if you talk, for instance, about density of a material, let's take density, however I make the size smaller and smaller, the density does not change. The density remains the same. Even if I have a very micro small portion of a material, it still has the same density. If I have to calculate the weight of a structure, a collection of components. Components are made of materials. I will show in a few moments. Yeah? Okay, but realize sometimes we're talking about properties, as I will also for materials today. You find more or less the same names for these properties also for structures. But realize that difference. Okay, well, here is a little bit your answer, I hope. Structures and materials are made from substances. Also, structures are made of substances. The question is, how? Well, first, if we have materials, the materials are retrieved, for instance, from ore materials like metals, or are made artificially by oil refinements. And these materials, they can be big blocks, they can be small pellets, they can be powder, they can be pellets, they can be blocks, whatever. These materials are transformed into so-called semi-finished parts. And semi-finished parts, think about, for instance, sheets, profiles, fibers, and so on. Yeah? From these semi-finished parts, we are going to create components, structural elements. And the structural elements can be a stringer, a beam, a sandwich. I showed some of them last time. And as soon as we assemble those, we obtain our structure. So yes, there is indeed a strong correlation between these two, but more or less via this route. Okay, let's zoom in a little bit in materials. If we look at materials, there are a number of main groups, to say so. First of all, we do have the metal alloys. And not all metal alloys are significant for aerospace, you will see later on. But this is a very big group. It contains steel, it contains zinc, it contains lead, it contains aluminum, magnesium, all kinds of metal alloys. The other one, which is often used in aerospace, are so-called composites. And a composite means composed of, you could say. It's composed of multiple materials, and I will tell later on how it is done. Fibers and resin, sometimes even metals are included, so then you have a hybrid material.
Some things are made out of duraluminum. What is that?
Again?
Duraluminum.
Duraluminum is some kind of aluminum alloy. You have, if you look at aluminum, you have plenty of different alloys. Every alloy has its specific features, its specific characteristics.
So things are not purely made out of aluminum.
Not pure aluminum. Pure aluminum is only used sometimes as a very tiny surface layer because it is very corrosion resistant. But the structure itself, the load-bearing structure, is always an alloy. Yeah? And aluminum is one of them, but that's an old name. Nowadays we have much more better alloys, I think. Okay, other main groups are, for instance, the polymers and the ceramics. And both are, at least for aerospace, not really relevant, structurally relevant. If you look, for instance, at polymers, and you have to think about plastics. Plastics are very nice materials for households, for gardens, for whatever, but you don't use them in highly loaded structures. Then the strength and the stiffness of these materials is way too low. Ceramics, on the other hand, has another problem. As you can see, it is way too brittle. It is very notch sensitive, and it breaks very easily if you have a load which is not properly applied to a structural part. I think I don't have any pictures from it, but remember one of the shuttles who was damaged by a piece of foam which hit the leading edge of the space shuttle, and later upon re-entry, you saw that the whole shuttle disintegrated because the heat could come into the structure and so on. That leading edge was made of carbon-carbon, and that's a special kind of ceramics. It's very strong, it's very heat resistant, but it is also brittle. So if you have an impact on a very specific way, very specific place, it could crack, it could damage, it could puncture a hole in it, and that happens in that case. The leading edge in that case was not designed for those kind of impacts. They were not anticipating. Only very small impacts could be sustained by that leading edge. But there you see, for instance, how a brittle material can be very nasty if it is not used in the proper way. Okay, let's have a quick look at some of these materials. First of all, I would like to look into metals. And as we all know, metals are derived from ore, which are retrieved from the earth, like this one. Here you see some very big cranes gathering the soil, and later on it is well, purified and alloyed. These two terms, purification and alloying, the first one means purification is that you try to remove all the materials you don't need. Yeah? So if you have, for instance, iron ore, that usually come in pellets, small bits of rock where the iron is inside, you try to remove all the non-usable materials. So extract the iron from it. And all the phosphor and sulfur which is coming to it, in many cases, should be removed. Purification. On the other hand, we would like to add a few things, in many cases, to get the right properties. There could be some chromium or some molybdenum or some carbon or what type of alloying elements we would like to need. We put it in. So if we have a molten material, first of all we try to get out all the unwanted stuff and then put in the stuff we want. That's the difference between purification and alloying. After that we do have a semi-finished material, and in many cases it is first casted in very large blocks. Maybe I have to trim a little bit of light. Come on. This is typical sequence for iron ore. Here you see very large blocks. I think they are about 2 meters tall and 1 by 1 square. So these represent more or less about 40 tons each. And you can still see that they are glowing from the heat. They are coming from the casting mill, casted in these type of shapes, put on here on lorries, and later on they go to the mill to be rolled out in thick plates or sheets. And then we have so-called semi-finished parts. Other options are also extrusions, profiles, and so on. From here we go to the final part. So when we have a sheet, we can press form apart from it. And then we have our component which can later be assembled into a structure. Okay, this is typical for iron. Question, what are the names of these processes used for aluminum and for iron?
Iron is the blast furnace.
Blast furnace, yeah, for iron.
I can't remember the proper name for aluminum, but it's the electrolysis.
Electrolysis, yeah. Yeah. So indeed, blast furnace and electrolysis. This is, by the way, a very energy-consuming process. In Holland, what you see, for instance, in Borselen, we have a nuclear power plant, and that was built there because next to it, in the harbor of Flushing, there was a very big aluminum plant. And a lot of that energy went into that plant. That's why it's also very important to recycle aluminum, because then you can get your new aluminum aluminum at much lower energy levels. Metals have a number of typical properties. First of all, most metals are isotropic. What's isotropic? Anyone knows? Again? They keep their shape? No, that's not meant by isotropic. I'm looking for another explanation. Consume heat and give it away? No, that's also not isotropic. Given the structure, and again? Critical properties are consumed or distributed? Yeah, you are becoming close. Actually, isotropic means that the material properties are independent from the direction. So if I take a piece of material and I determine the strength in this direction, it's identical as in this direction or in that direction. Same with the stiffness. Of course, also the material is homogeneous, so the density is the same everywhere. That means isotropic. Yeah? Properties are independent from the direction which I take in the material. Okay, most materials are indeed isotropic. The strength we obtain usually by alloying and heat treatments, putting in materials and do some heat treatments, that will be told later. Most metals also do show plastic behavior, and what it has, plastic behavior has a very beneficial advantage because we can shape a product from a flat sheet. Here you see, for instance, a simple tool, simple cutout, and after press forming operation, this is the final part. You can do that in one stamping operation. That's due to the fact that the material is plastic, can become plastic. And then, last time we have said, we operate our aircraft in the elastic area. Please don't go into the plastic area because then you have a lot of troubles with flying around. But manufacturing is done in this part. So this, what you see here, is related to the plastic area. Yeah? Metals can also be melted, can be made fluid. And it also has some impact on, for instance, recycling, welding, casting. Good processability and often low cost. Not all metals are cheap, but a lot of them are cheap. Next slide, you see some properties of metals. Well, just to show you, first of all, the density has to be related to the weight. Then the Young's modulus. You already had some information about these properties or not? Some yes, some no. Well, it has to do with the angle of this one. The steeper the curve, the more resistant the material to deformation, and the higher the Young's modulus. The stiffer the material. Stiffness means resistance to deformations, and the stiffer a material, the larger the force I need to give it some deformation. Yeah? So that's represented with this number. So steel has a high stiffness when you compare it to aluminum. And titanium, for instance, here is some intermediate value. Yield strength, as you can see here, that's this point. The transition from elastic into plastic. So during operation, I always have to stay below that. And when I would like to manufacture by plastic deformation, the previous slide, I have to go beyond that point. Yeah? Failure strength is the maximum strength here, and the maximum strain is actually, if I do this as stress-strain curve, the maximum deformation I can take. Well, what you see here are stresses and strains. Why stresses and strains? If I would like to compare two different materials, like let's say aluminum and steel, I can take two samples. Once, well, no, two bars. The aluminum is a thick bar, the steel is a small bar, a thin bar. When I pull them apart, then I see, okay, the aluminum fails, let's say, at 10 tons, and the steel fails at 3 tons. So the aluminum bar is stronger than the steel bar, but it does not say something about the material itself. If I would like to compare aluminum and steel, I have to do a specific calculation. I have, in tension for instance, I have to take the load and divide it by the cross-section of the bar, and then I get a so-called stress. Force divided by cross-section is a stress. And because the aluminum is much thicker, the stress will reduce significantly. And because the steel one was a small one, it could have a higher failure stress than aluminum, which is often indeed the case. Yeah? And then I can compare the two materials and say aluminum has a higher failure strength or lower failure strength than steel. Is that clear? Well, that's how we compare these materials. These are all in stresses, so we are actually here comparing materials. Well, what you see, for instance, is a difference in density, steel, aluminum. Here you see density of titanium. What's more, this is a high-strength steel, and you can see it has a very high value indeed. So based on these tables, what material would you choose for a high-strength application? High-strength steel is one of the best, huh? Okay. Is it also true if we are going to fly with it? Yes, no, that's an interesting conflict.
You need something more elastic so it's more resistant.
More elastic, should be lighter. How are we going to incorporate the weight? Is that possible? Let's say we are talking about tension. We're pulling at a material, so it has a certain force divided by the area we enter up to a certain stress, but the bar also has a certain weight.
So take whatever has the lowest density, so it also has the lowest mass.
Again?
Take whatever material has the lowest density, so for the same area, it'll have the lowest mass.
Just taking the material with lowest density?
No, for just that application.
You have to take some parameter which has the performance and the weight in there. Well, if you calculate it for tension, you actually get the stress divided by its density. And that's what we call specific stress, specific strength, specific yield stress, and so on. Realize this is also only for tension. If you go, for instance, to bending, or if you go to compression, you can have different ratios, different formulas for the stress and the density. But for this simple application, pure tension, and I challenge you to look for it at home, simple tension, you can have stress divided by density. Well, if you do that, you find these numbers, and that's what we call specific values. Now, what's now very striking here is that, first of all, most of these specific densities, specific stiffnesses, are more or less identical. If I go back, here you see large differences, but this large value is also divided by a large density. This is almost around 25. But more interesting are, of course, these strength values, yield strength and failure strength. And now what you see, high strength is still maybe the highest, but not by that huge difference as on the previous slide. titanium here is also coming very close, and also this aluminum is coming very close. So now if I have to design a structure, I will not only look at these specific properties, but also look, for instance, at thicknesses. If I need a specific force and this ends up with a thickness of 0.3 millimeter, that's very thin. So that will be very vulnerable, for instance, by handling or also by impact. Aluminum probably will be about 1 millimeter if you compare it. Titanium maybe 0.6, 0.7. That's much more rigid, much more sturdy to impact and these kind of things. Yeah? So if we compare materials for aerospace applications, we often look at so-called specific properties. Not just at the basic properties, but specific properties. Because we have to fly. And again, this is for tension. It's the most simple formula. You get these kind of formulas. Property divided by density. Is that clear? If not, raise your hands. Okay, then I can speed up a little bit. Next group is polymers. As I said before, polymers are not very interesting from structural point of view. And still, I would like to have a quick look at them. Because polymers are one of the major ingredients in composites. Some specific properties of polymers are also influencing my composites. Two main groups, thermoplastics and thermoset polymers. Thermoset polymers are made by reaction. You have two components, you bring them together, they react, make a molecular network, and that whole process is irreversible. You cannot turn it around. So once you have cured your polymer, the shape cannot be changed anymore. That's different with a thermoplastic. A thermoplastic is made of large molecules with with some weak bonds between the molecules. Some kind of spaghetti. Yeah. At room temperature, it's rigid. It is, you can use it, but heat up the temperature, and the bonds between this spaghetti is disappearing. It becomes more fluid. So you can reshape it, and you can redo that frequently. So thermoplastics can be softened. It's reversible, and it's made of one component. And thermosets, you have curing, irreversible, and so on. Here you see some foil and some materials made from thermoplastic and thermoset materials. Again, polymers are isotropic, but they have a very low strength and stiffness. And therefore we don't use them unreinforced. Pure polymers are not useful for structures. Large variety, again also plastic flow. This is, for instance, a setup for injection molding. Here you have some polymer put into it, and then by a turning screw and heat, you force the molten liquid material into some cavities here, cool it down, and you have another two parts. All these plastic coffee cups we have, but also plastic chairs and furniture for the garden are all made by injection molding, this process. Tooling is usually very large, but since you have huge quantities, it's not really a problem. Good processability, and in many cases cheap, very cheap materials. Okay. If you have thermoplastic materials, you bring them two together and you have a local heat source like a laser. You can locally melt them, push them together, force them together, and you get a weld. Just as it has not really become fluid, not very water-like material in between. It is some paste material. Whereas in metals you really make it fluid, you really make it liquid. But indeed it is some kind of welding. Local heat source and pushing together and you have a weld. Okay, polymers, composites. Composites are made of polymers and fibers. Many different type of fibers are available: glass fibers, aramid fibers, carbon fibers, dyneema fibers, and so on, and so on, and so on. Boron. Short, long, and continuous. We mean with short only a few millimeters, and with long a few centimeters, and with continuous, well, at least a meter or longer. Most of the high structural parts, the high performance parts, are made by continuous fibers. Because those can be oriented in a certain direction, the other ones cannot. In many cases, in components with short and also with long fibers, the fibers are more or less oriented at random. The direction is not controlled. That's possible with the continuous fibers, not with the short and long ones. Hybrid materials, that's actually polymers, fibers, and metal layers. That's sometimes called a composite, sometimes called a hybrid material. Well, here you see some examples of weaves. You have many different weaves in the industry. Tenkate, as you can see here, the emblem of the company, is a main player in that domain, in composites. They shift from cloth to composites, and I think they did it very successfully. But here you see, for instance, a number of these weaves coming from Tenkate. In many cases, yellow is more or less, for most reasons, if there's no resin to it, it's aramid, white, glass, black, carbon. So you can recognize most fibers. It's not always true, but as a rule of thumb, you could say so. And here you see a picture of a fiber metal laminate. Metal layer, composite layer, metal layer, composite layer, metal layer. And these layers are very thin, in the order of magnitude of 0.3, 0.4 millimeter. So very small. If you look at composites, I would like to explain a little bit the principles of composites. Realize the fibers are the materials in there which are strong, which are stiff. And for the strength and the stiffness of a component, these materials are sufficient. But as we have a rope, we can pull onto a rope, but we cannot compress a rope. As soon as you have a fiber, you can tension it, but not compress it, because then it buckles in all directions. That's where the resin comes in. The resin is there for supporting, making able that you also can have compression forces on composites, and of course also to protect the fibers, so that no moisture or whatever can degrade my fiber. But the strength and the stiffness is provided by the fibers. Fibers are strong and stiff in one direction only. Yeah, if you have here, these resemble the fibers. This thin layer of fiber composite has strength in this direction only. In the other direction, the strength is related to the polymer, and as I said before, that strength is, well, rather low and can be more or less neglected. If I also would like to have strength in this direction, I have to build up so-called laminates and put layers in different directions. Yeah? Okay. Some features of polymers: highly anisotropic. That means now the properties do depend on the direction I will look for. It has also a benefit. If I do have a A strip like this, if I have a strip like this, and the main load is in this direction, length direction, I can put most of my fibers there, in that direction. Very little amount of fibers in that direction for coherence, but most of my fibers can be in that direction. Then I use very highly efficient my material. This is a metal one. It is as strong as this direction as in that direction. In that direction, I don't use that strength. So it's over-designed more or less. That's why how composites can be sometimes very lightweight. It's a layered structure, high strength stiffness, low density, no plasticity. Processability is also rather good, and you can make nice parts of it. Sometimes made in laminates. Ja. It's too fast. Yep. Made in laminates, just like metal sheets, more or less, like metal sheets. And sometimes it is made in sandwich materials. Either a honeycomb core material or sometimes a foam core material. Here you see, for instance, these flaps on an aircraft are in many cases partly or sometimes even completely made of sandwich materials. And here you see how it is constructed. Boeing 787 is a new aircraft, I think entering service within a couple of months, I expect. A lot of it is made from composites. The fuselage is almost entirely made of composites. Well, here you see the inside. All kind of head stiffeners in this case, some beams, and so on. Okay, let's have a look at the properties of these composites. I put in this one several materials. First of all, an epoxy. Epoxy is a thermoset polymer. It's polymer only. And when you see the Young's modulus and the strength, and you compare that with the aluminum values here, you see what I meant when I said these materials have very low strength and stiffness properties. PEEK is a thermoplastic material. Polypropylene is also a thermoplastic material. And you can see all these materials have low values for strength and stiffness. Here you have two materials, two metals to compare with, because we have seen them a few slides ago. And these are two composites. One a glass composite and one a carbon composite. Both have unidirectional fibers, so all fibers are running in one direction, and we are testing the material in fiber direction. So realize, as soon as you are going to a cross-ply material, or you have to divide these values by 2. 60% means the fiber volume content. How many fibers are in there? This is a rather high value. What you often see, for instance, for injection molding or hand layup, you enter up with values in the 40 or 50%. But it has a number of quality of your product. So the higher the volume, the higher your properties can be. Well, if you compare it, you can already see that glass is very strong, carbon is a little bit less strong, but that changes when we are going to the specific properties again, as you can see here. And then you see that these composites can have very high specific values, both in stiffness as in strength. Again, realize we are talking here about unidirectional materials. As soon as you have to make a component which is loaded in more than one direction, these values will drop. But nevertheless, you have potentially very high valuable material. Again, the yield strength of these materials don't have a yield strength. If you have a composite, those are more or less elastic until they fail. So usually these composites don't have a specific defined yield strength. Yeah? Yield strength is typical what you often see with metals when you go from the elastic into the plastic area. But it is not happening in composites. Yeah? The maximum strain? The maximum strain, that means how far I can stretch a material before it fails. And there you see one of the weak points of composites. It is very brittle. It has a very small amount of deformation possible before it fails. That's for metals much better. Yeah? Okay. Some space materials, some special materials. For instance, space materials. I will come back to that later on. But for space materials, this is a very important relation. The heat coming in and the heat flux going out, and how to dissipate, how to cooperate with heat. Okay, I think it's better now for a short break. Here before the break, and of course we'll continue here. I'm behind schedule, so I will try to speed up a little bit. I'm talking too much. What I would like to show very quickly is that there's a relationship between the materials, type of material, between the shape or the design, and how it is produced, what kind of production methods you have. Well, last time I already told you that if you look at the Greek temple, nobody assumes that that is made of steel. Yeah?
Look at a what?
Made of steel.
Look at a what? Mm.
Also, this Eiffel Tower, as you can see here, we see the shape, we know also what kind of material it is made of, and also what kind of structure. It is typical truss structure, made of steel. So there is a relationship between manufacturing processes, material types, and shapes. And there are a lot of combinations possible. Not every combination is possible. Think, for instance, about fiber-reinforced polymers, composites. You cannot cast them. You cannot pour them into a shape as a liquid. So there are also possibilities which are not in there. But a lot of other ones can. And if you look at those, you see that there is a multitude of processes which can be used. Well, I just will show quickly a few of them. For metals, for instance, we can have casting, forming. Those are two very famous and very favorable processes. Here you see, for instance, this aluminum casing for some wheels in there. This one is made by a casting process. A metal can become liquids. If you heat it up, it becomes liquids, and we can pour it into a die, cool it down, solidify it, and then we have a shape. And you can see we can have very complex shapes. Metals can also be machined, cutting away material. Here you see, for instance, some kind of bracket for an aircraft. This is machined, completely machined from a block. You take a block, machine away about 90% of the material, and you enter up with your final product. Usually done on big milling machines.
Why isn't it possible to cast some brackets?
You can also cast it. Yeah. This shape can also be cast, can also be forged, but then you have to balance, you have to make a trade-off, which is most beneficial from point of costs, from point of performance. Yeah, but it's possible. You could also cast it.
How would the way of manufacturing affect the performance? How would the way of manufacturing affect the performance? Because in the end, it's sort of.
If you cast, for instance, if you would cast a structure like this, the microstructure is different. And that can have an impact on, for instance, fatigue, for instance, on corrosion. So, from corrosion point of view, fatigue point of view, this could be better. Not always, but this could be better. Yeah. Forming, all kind of different forming operations, starting with a flat sheet and then form it into all kind of shapes. And finally, multitude of ways to fasten each other, to assemble structures from these components. Riveting, welding, forming, squeezing, and so on. Composites are different. Composites are in many cases coming in layers. Layers of fibers in weaves, fabrics. Sometimes even the resin is already brought onto that weave, and then we have a so-called pre-preg, pre-impregnated fabric. Pre-preg. What we do in composite manufacturing is building up a structure by putting layers on top of each other. For instance, in the layer process. Once the whole stack is completed, you put it into a nice foil, into an autoclave, and cure it. And after 1 or 2 hours curing, you have a solidified, a cured product which can be used in an aircraft. Here you see, for instance, parts which are made by press forming, just like metals. Here we have, before this press forming operation, we do have flat laminates of thermoplastic materials. These are cut into the right pre-shapes and then press formed. And before the forming operation, what we are going to do is we heat the material to make the thermoplastic soft, so it can indeed form. It's only possible for thermoplastic materials. Well, these are typical ribs, as you can see here in wing structures. Filament winding, also possible, or by rovings, some kind of ropes, very thin ropes, and sometimes even with tapes. This is made by filament winding or tape laying, and this also. So summarizing, if you look at the different properties, that has an impact on how to produce it. Metals have plastic behavior, and that means you have also damage tolerant and joining. You also can have forming operations. Composites, what kind of properties they have, and here you see some impacts on manufacturing. Sandwich, different cell, laminating, and so on. Okay. Questions so far about this one. Realize the main message I brought in the last 5 or 10 minutes was that there is a link between your material, the shape you can get, and the production process.
What type of exam questions we can get, or it's more basic knowledge?
What type of exam questions can you get, or is it basic knowledge? You should, for me, most important now is understanding. So if I have a multiple choice question and say casting can be performed in metals, composites, hybrid materials, you should be able to say, okay, it's okay for metals, but not for composites. Yeah? As an example. Or I would ask you, for instance, to mention at least 2 production processes for composites. Then you could say layup and filament winding and so on. Yeah? Okay. This one is a little bit about exploring the limits. I forgot here to mention what chapter it is, but I will put it on later onwards. Later on. Hello? Yeah. Later on, I will put it again in the slides. Yeah. So when I put it on Blackboard, there will be some Anderson chapters or paragraphs in there. This is about X-planes going from subsonic to supersonic, and if I have some time, also a few words about high temperature materials. X-planes means experimental. And after the Second World War, there were a huge number of experimental planes, and I think they are still going on. And each of these planes has some specific goal to investigate some specific property. One of the first, and which was most famous, I think, is, for instance, the Bell X-1, which you can see here. The first one who flew faster than speed of sound. They conquered there the supersonic, or the so-called sound barrier. You see, it's only just beyond speed of sound. As I said, a lot of these X-planes have been produced after the Second World War. If you look on this side, you can see a large overview of all kinds of X-planes. I think one of the latest, and maybe that's already obsolete, I don't know. I think they are somewhere in the X-53 or something like that. And I will show a few of them and just mention how they use them to explore the limits of flying. First of all, the X-1 was to conquer the sound barrier. Here you see another one, X-1A, X-1B, derivatives of the X-1, the Bell X-1B, flew a few years later, and they exceeded even Mach 2 times speed of sound. Expensive projects in many cases, because as you can see, these aircraft only flew a few times, 15 flights and 27 flights. Well, that for a very expensive aircraft, it is also a very expensive program. Another one, in 59 already, that's more than 50 years ago, that's the X-15. And you see a picture of that aircraft here. So far, the aircraft with the highest Mach number, 6.7, sorry, that's my Dutch habit, and also very high altitude. Yeah. Temperatures on this aircraft exceeded 600 degrees Celsius. So that's not flying around anymore with aluminum. You need to have steel or titanium alloys. Very expensive aircraft, again. X-29, specific aircraft for forward sweeping wings, as you can see here. Most of the aircraft have the sweep backwards, and that's due to the fact that we are constructing in aluminum. As soon as you have an increase in alpha, you also have an increase in force, and since that point is behind the attachment point of the wing, you will have also a forward bending moment in your wing structure. So the initial increase in angle of attack is counteracted by a twist, forward twist in your wing. As soon as you do the opposite for a metal structure, you have an increase, which is indeed further increased by your bending up of the wing. So forward swept wings using conventional structures are not possible. Composite, however, you can tailor. You can tune the materials, the properties you like. So in this case, the structure has been tailored such that even in a forward swept wing, with a bending up, you still have a forward twist of your wing box. Yeah? That's possible with composites, structural composites, and not with metals. 31, thrust factoring and maneuverability, flying at very high angles of attack, trying to break more or less the stall barrier. And see what happens if we fly very close to that. 32, 35, that's nowadays what we call the JSF. This is our JSF fighter nowadays. But it started as so-called X-planes. Competition of an aircraft who can take off on a very short or even vertical position. Short takeover landing or even vertical takeover landing. In one aircraft. That was the challenge, to come up with concepts for that. Yeah, Harrier also did, but this is a new generation of aircraft for it. X-45, that's an unmanned combat vehicle, one of them. I think there are several X-planes in this domain and still developing further. Well, that's just a very rough overview of X-planes. I would go back to the first X-planes because then we were struggling with the speed of sound, the Mach number. Yeah? Who built the X-planes? That's usually with different companies. So sometimes it's Grumman, sometimes it is Rockwell, sometimes it is Boeing. Usually there is some kind of competition between companies, but actually this is maybe nice to tell very briefly. The United States are often blaming Europe for getting subsidized manufacturing of aircraft. They said, well, the government spends a lot of money, give the companies in Europe a lot of money. And that should not be done, because that's frauding the competition. Europe, on the other hand, says the United States defense, for instance, gave a lot of contracts, for instance, these ones, to aircraft companies in the United States, which they can use to develop their knowledge and their technologies. So that's also kind of subsidizing. There has been a long struggle in there. I don't think it is still over yet. But that's about company who is giving it, not just one company. Speed of sound. For the speed of sound, we often use the so-called Mach number. The Mach number is defined as the velocity, the true airspeed of the aircraft, divided by the speed of sound. And the speed of sound, if this number becomes 1, we are flying as fast as the speed of sound. And then we have a sonic flow. We are flying sonic. Beyond that, it's supersonic. Below that, it's subsonic. Well, this is one very strict division. We often use also a division like this. You have a subsonic below Mach number 0.8, 0.9, transonic in the regime of 0.8, 0.9 to 1.2, supersonic from 1.2 to 5, and hypersonic beyond that. Well, let's have a quick look what that means. If we fly sonic, the speed is smaller than my speed of sound. So if I travel from here in this direction, the sound progresses faster than what I'm flying. So what you have here is densification of the sound, here less density. So you have that typical Doppler effect. When something comes to you, hear a high sound. When it's past you, you have a low sound. That's represented in the density of these lines. Doppler effect. As soon as we are flying Mach 1, you see a coalescence of these circles. And you get more or less a shock wave here. The pressure before it is lower than the pressure after it. And it becomes even more significant when you're flying supersonic. You get these so-called shock waves. And the shock wave is nothing less than the pressure difference. So when I'm standing on the ground and an aircraft is passing by, flying faster than the speed of sound, I hear a bang, and the bang is a pressure difference. just before hitting me, the pressure is lower. As soon as this passes, the pressure is slightly higher. And that gives me a bang in the ears. Yeah? So we perceive it as some kind of bang. You have a coalescence indeed of waves. You also see here a angle, mu. The speed, mu, yeah. What's the proper English pronunciation? Mu. Okay, mu. From now on. Okay, mu. Well, here you see the velocity. Here you see the speed of sound times a time interval. And this angle is representing, of course, my Mach number. The sinus of that mu is the reciprocal of this Mach number. Seems very simple, but sometimes you can also use it to calculate speeds. This is an aircraft flying through the speed of sound. And due to, well, I'm not a meteorologist, but due to pressure differences before and after, also differences in, no, that's too complicated, but you will see some condensation behind the shock waves. Yeah, and that's due to the difference in pressure and density and so on, temperature. Temperature, pressure and density changes over that wave, and that makes it visible like this. When you see this, you could ask, what is the speed of this aircraft? And actually what we use is the same mu as we have discussed on the previous slide. Because there's an angle of about 30 degrees. So our mu is about 60 degrees. The sinus of 60 degrees is about 0.87. That means the Mach number is 1.15 order of magnitude. If he flies at sea level, this is my speed of sound. So the true speed at that moment is 390, or about that in kilometers per hour, or that in knots. Yeah? So just calculating based on this one. Well, here you see what the real values of A should be, but at sea level you can fill in the sea level values according to the standard atmosphere. Well, here again you see another picture, and this is, I think, a bullet or something like that, pictured. This is almost, I think, 30 degrees, 40 degrees, I don't know. But again, you can calculate the speed of sound, or the true speed, if it is flying on sea level. On the internet, again, there are a lot of nice short movies about aircraft flying supersonic. And this one, I think, is also always a very nice one. Have a look at it. Some. I cannot hear you properly. What happens if you break the speed of sound underwater? My goodness. I don't know. I think... I really don't know. First of all, I think there's a completely different speed of sound. That's one. And also the density of the material is completely different. But nice question to ask when you are going into aerodynamics, and ask the aerodynamics people about it. Yeah? Again? Is the sound barrier is this cloud all the way existing, or does it... no, go back please. Maybe I can... try to see where I can get it. Come on. Once more. I hope that answers your question. Sir? That answers your question? Because an aircraft is not just going through some shock waves. No, it's flying around and dragging with it these shock waves. So his question was, does you see this cloud only once when it passes through? No, it takes it with it. And of course it depends on the composition of the air whether you see a very significant cloud or not. I can imagine that when he's flying at higher altitudes, but then the moisture in the air is much less or drier or whatever, you do not always see such a cloud.
Why is there another cloud?
You also probably have some shock wave over there. So you have a small shock wave here and a much bigger one coming from the wings. Last question.
One last question. If you're slipstreaming behind this aircraft when it's going supersonic, would you actually be pushed away from it?
I don't know.
Because like you said, there's a shock wave coming through the pressure difference. So if you're slipstreaming behind this aircraft, would you be pushed away instead of closer?
Again, ask these aerodynamicists. Yeah? Okay. Just a few words more about this. This is what happens when flying faster than speed of sound. We have seen before that at very low speeds you can regard the air as incompressible, but that's not possible if you are flying faster. So let's say 300 kilometers per hour, 350, it's up to then you can regard it incompressible. And for most general aviations, that's the case. For civil aviation, military aviation, you are always in this regime and you have compressible airflow. This is what happens. You have a speed and a Mach number, a pressure and a temperature before, and after a shock wave you see that these are changing. The speed here is smaller, so also the Mach number. The pressure is slightly higher, and also the temperature is somewhat higher. So after a shock wave, pressure and temperature increase and speed decrease. Sometimes you can also experience shock waves even when you are flying subsonic. Depends a little bit on the airflow over your wings. So sometimes very close to the Mach is 1 number, you can have already some supersonic flow and closing with a shock wave. Or sometimes if you have tried to fly around with these kind of profiles, typically for subsonic speeds, you can have a very big shock wave in front of your wing. And these are very detrimental for your drag. Here you see what happens with the lift over drag ratio when you're coming close to the Mach number. This dotted line is for a simple aircraft with such kind of wings and straight wings. And you can see you have a high lift over drag ratio, but it plummeted to 0 as soon as you come to the Mach is 1 number. That's different for a aircraft with a swept wing. Though smaller LOD values at small speeds, it has a much better one at high speeds. And these sweep angle aircraft play around with that. So they can change their wing plan during flight. So almost like this at low speeds and like that at high speeds. Here you see, for instance, again, the same effect, where you have drag coefficients, which is low at subsonic speeds, but increases significantly when you come close to the speed of sound. And that's why people always experience as some kind of sound barrier. That is almost very difficult, problematic to surpass the speed of sound. You also get a lot of buffeting, trembling of the wings. So they were, in the early ages after the Second World War, very anxious to go beyond the speed of sound. That's why the Bell X-1 was launched. No sweep, you have a huge increase in drag, and if you have a very proper sweep, you have much lower. So it helps because, first of all, if this is the true airspeed, the real airspeed flying over the wing becomes smaller when you have a sweep, and sometimes even your angle, your whole wing, can be staying out these shock waves. And then after the second shock wave, still your whole aircraft is flying subsonic. It's dragging along a lot of air. Well, here actually more or less a similar story, where you have, let's have a look. These are points for this configuration, these are points for that configuration, and here are the points for this configuration. Typical aircraft, Tomcat, Tornado, which have a variable sweep. Okay, so in the transonic regime, close to the speed of sound, close to Mach 1, you have in many cases a very high drag. At supersonic speed, you have maybe a lower L/D ratio, but a much higher speed. So the dynamic pressure is compensating for that. I don't know how many people have seen this in real life, this aircraft. It's a Starfighter. If you come close to it, you see how astonishing small wing surface it has. It's really a very small wing. That means, for takeoff and landing, you need very high takeoff and landing speeds, and also very long landing strips. Yeah? So the runway should be very, very long, usually in the order of 2 to 3 kilometers. Nowadays, you see, for instance, a lot of new aircraft like F-16 and F-18 and so on. They can take off within a very much shorter distance, but they have indeed an increased wing surface. This aircraft has an astonishingly small one. Okay, few words about high temperature materials. If there are no questions about this explains story and Mach numbers. We have seen already this aircraft, that was the X-17, which was flying through the air with very high speeds, Mach 6 and beyond. Sometimes I'm stumbling over the words, nevertheless. Had indeed very large temperatures, 600 degrees or even more. And that means we cannot use aluminum anymore. We need to have stainless steel, titaniums, and so on. Here you see, for instance, some of these materials. Aluminum, titanium, stainless, Inconel. In particular, titanium is for those applications a very good material. It has high strength, high temperature possibilities, and is still not too heavy. The density of titanium is 4.4, 4.5, whereas for stainless steel and Inconel it is 8 or beyond. So that's very heavy. Inconel is a special steel, nickel, chromium alloy. So it's a mix of these elements. And that's often used as a special high temperature alloy for space applications or for applications like this one. We often have to look, if you look at the properties, we also have to look, of course, at the temperature relationship. And here you see, for instance, temperature relationship of titanium alloy. This is about room temperature. And here you see this is about 540, 600 degrees. So the strength decreases by a factor of 2. You have to keep that in mind if you are designing an aircraft like that. Yeah? Another one, Blackbird. It is made of titanium for more than 90%. It flies at Mach 3, so very high speeds. Temperatures of the leading edge up to 400 plus degrees. So that's also rather hot. I said titanium is a very nice material from property point of view, but from manufacturing point of view, it's really a very difficult material. It is difficult to form, it is difficult to machine, and also welding is not that easy. So indeed, titanium is an ideal material, but from manufacturing point of view, costs a lot of headaches. But as you can see, we can manage. We can make these aircraft and fly them around. Leading edge of 400 degrees, still not capable of aluminum. If you look at the Concorde, you see here in the notes, Concorde was made for a Mach number of just over 2, because in that case, the maximum temperature could be kept about 120, 25, and in that case, we still could use aluminum structures. So there's here a decisive link between the temperature and the use of materials. Well, if you go into space, you enter into completely different materials. Well, completely different, but you have different requirements for materials. One of them is, for instance, these heat shields. These are completely different materials. In the early ages, they use so-called ablative shields, and that means that when it enters, all the heat dissipates very little material, but by dissipation, a lot of energy was consumed by the dissipating material, by the sublimating surface. And that is still used nowadays, was also used in the space shuttle, for instance. This is a heat picture of the space shuttle. Leading edge is here, and also the nose up to 1650 degrees, and that requires special material. For instance, I mentioned already carbon-carbon, reinforced carbon-carbon. Nose cap, winning leading edges, where temperatures are very, very high. But these materials are also very brittle, as we have seen with one of the accidents. Yeah? A lot of tiles are used on other areas where the temperature is not that high, or insulation blankets. Here you see, for instance, one of the tiles. The tile has a foam-like structure in between, so it is very much isolating the inner structure. Takes up some heat, but there's a lot of silica. Well, here you can read what kind of materials are used. The fun from of these tiles is those were most of them were identical tiles. So there were maybe a few thousand of these tiles on the aircraft, every one more or less different. So it was very complicated and very costly. Well, here you see the distribution of all the different materials. So the hot structure here in front, the carbon-carbon, the tiles, this area, the blankets, and so on. Okay, so that's something about these special materials. I'm at the end of this second hour. First I started with some explains. You see some speed records, some altitudes, but that means also flying at high speed you need to have special materials, and sometimes very weird materials. Questions from your side?
Was the airplane that holds the record
X-15. Yeah. More questions? Have a good appetite and see you at the studio classroom.
Please visit our OpenCourseware website for more information. See you at our next podcast.